And given the conditions, that's pretty special because Teton Gas is closed, Teton Village has no power.
What?
The highway down through the state was closed this morning, and we're in the middle of a major storm warning, or while it's happening. So, at any rate, so we're here.
Thanks for showing up, everybody.
So you can tell us about the weather there.
Thanks.
It's beautiful. It's gorgeous. The oceans are calm. The sun is out. It's warm.
Shut up!
All right. If you would introduce yourself to our audience and get this on the way.
Absolutely. Thank you, John. My name is Lucas. I am one of the education outreach officers here on board the Research Vessel Atlantis. The other education outreach officer is Teresa, here, who will be mainly behind the camera today. And it gives me great pleasure to introduce to you our chief scientist and a professor at UW, Dr. Michael Cheadle. I'll turn it over to him now.
Hi, John. Hi, everybody.
Hey, Mike. How you doing?
So, welcome. I'm doing well. You know, as you were saying earlier, we're sitting here in shorts and...
Whoa!
Uh-oh, that's this, sorry. That's this cable.
So, what we'd like to do today is, give you a flavor of what it's like to be on a U.S. research vessel. We're currently sitting on the RV Research Vessel Atlantis. Atlantis is one of 4 U.S. global class research vessels. And global just means that it can go, it's got capacity to go to any ocean anywhere, pretty much, apart from it's not an icebreaker. And this one actually has the manned submersible housing, which we're not using. We have the US's remotely operated vehicle, which goes to the bottom of the ocean on a tether, and an autonomous vehicle called Sentry. We'll talk more about that in a minute. And so to give you an idea of what we're going to do, I thought I'd give you a little lecture for maybe 15, 20 minutes, which basically tells you why we're here and shows you some pictures, tells you about the questions we're trying to answer. And then Lucas and Teresa will take you on a tour of the ship, and you'll see some of the vehicles. The moment, we're just at a desperate moment between operations. The ROV came off the seafloor now, basically half an hour ago. But they'll show you around, and then we'll show you a little video of all the highlights of launching submarines and so on and so forth. And then we'll have a question and answer session if you guys have questions. So that's the kind of plan for what we're going to do. And Bobby will be in later as well for questions.
Sounds good.
So, slideshow. Okay, so the nice thing, joking this side, and I do feel for you guys, and when we actually came out, it was -20 in Laramie, so we went through a 100-degree temperature change. But the place we came to was Easter Island, which is not a bad place to start. And here's a picture I took of, the typical Easter Island picture. So the question becomes, though, why do we come all the way to Easter Island, which really is practically in the middle of the Pacific Ocean? We really are a long, long ways away from anywhere. But the reason we came here is 200 nautical miles to the northwest of Easter Island is this place called Pito Deep. And the literal translation for Pito Deep is the belly button. So we're at the belly button of the Pacific Ocean. And if you look close enough in the middle there, and I hope you've got enough resolution to see it, there's actually a little tiny volcano. You see a little bump in the middle of the bubbles. So it really does have a belly button. But what it represents is a big crack through ocean crust. And so the deepest part of that picture, what you're looking at is the bathymetry of the seafloor, so the topography of the seafloor. And the deepest part is at 6 kilometers below sea level. I don't know whether you can read the scale, but the purple at the bottom is 6 kilometers. And then at the top, the reds are about 2 kilometers.
Resolution is good, Mike.
Good, right? So what this affords us is it gives us literally a 4-kilometer deep slice through ocean crust, and that really is why we're here. And the next slide kind of puts the context in that here's a picture of the whole, of the eastern side of the Pacific Ocean. It's a topographic map. You know, here's the East Pacific Rise. Sorry, I put my pen on and I always forget. There's the East Pacific Rise. And so you can see from the colors that it deepens away from it. And the real reason for putting that map up there, as many of you know, the seafloor itself is covered by sediment and below that basalt. And there's actually very, very few places in the world where you get these cracks that allows you to get, you know, beneath those surface features. And so if we move on to the next slide, which is a cartoon, here's a cartoon of the same, or a smaller part of that same map. Here's the East Pacific Rise again. And we're at this place called Pito Deep here. There's another place called Hess Deep, and another one called Endeavour Deep. And these are probably the only 3 places in the whole of the Pacific where you've basically got a crack in the mid-ocean ridge that allows you to get this cross-section. And the picture on the left is the cross-section through ocean crust. The brown stuff on the top are the basalts, you know, which cover the rest of all the oceans. The grey stuff are the dikes, that, if you like, the feeders from the magma chamber to the erupting lavas on the surface. And the yellow stuff is the gabbroic layer, and you can see from the scale, which is on the order of 5 to 6 kilometers thick. And because it's buried by this stuff, we know so little about it. And so you can guess, you can see my picture, I put on this red box here. Basically, Pito Deep allows us to sample rocks through that section shown by the red box. And that's really why we're here, because we actually know so little about how this yellow stuff works, the gabbros, which effectively are the frozen magma chambers that form ocean crust. And then just to point out, we have the mantle beneath. But basically our target is looking at this part of ocean crust. So that's why we're here. And the next question is basically, why is there even a crack here? Oops, sorry, I'll get with the system in a minute. So the next question is, why does Pito Deep exist? And here's a zoom in on the East Pacific Rise. So it's just a zoom in on that picture we had earlier. Here's the East Pacific Rise. But Pito Deep is just here. And what these black rings are little microplates. And they're microplates because, I'm going to clear that screen, what's happening is the East Pacific Rise is overlapping itself. So the East Pacific Rise is doing that. And what you've got is a little bit of tectonic plate that's kind of caught between the 2 arms of the East Pacific Rise, and it's actually rotating like a cork. This overlapping process leads it to rotate, and as it rotates, you basically get cracks, which is why Pito Deep's here. And you know, the thing that I haven't mentioned is all those black dots are earthquakes. So that's another way we know these are plate boundaries. And then this one's the Endeavour microplate I mentioned earlier. So, you know, there's about 3 of these microplates on the East Pacific Rise. And if we turn to the next page, which is just a cartoon, here's a cartoon of the Eastern microplate. Remember, we are here at Pito Deep, which is, you know, the crack on the corner. And then here's the East Pacific Rise coming this way and coming this way. And the plate is kind of stuck in the middle. And the black lines that you can see are actually magnetic stripes, and they give a clue to what's happening. If you look at the stripes down here, they're kind of in this angle, and then you can see them rotating. And what's really happening is down here, you know, we've only got one ridge, and so that's spreading at 14 centimeters a year. And up here, we've only got one ridge, so that's spreading at 14 centimeters a year. But in the middle, we've got the overlapping ridges. And so in between, the spreading on this side and this side must add up to 14, but both of them are spreading less than 14. And so I'm going to clear that mess just to illustrate the point. So the point is, and I'm going to do it by drawing arrows, here we've got a spreading rate of 14 centimeters a year. As this thing dies out, at the tip of it, we've got a spreading rate of 0 centimeters a year. So hence, the bottom spreading faster than the top, which leads it to rotate, because the bottom is moving faster than the top. And that's why this thing's rotating. So that's why Pito Deep is here, and why we get this cross-section. And so the next thing to move on to is, well, what are we actually doing? What are the questions that we're trying to answer? And the key point is, as I've said now several times, is Pito Deep provides the third dimension. And so that allows us to answer questions like, what is the composition and the nature of oceanic crust? I.e., what's that gabbro layer look like? What kind of rocks is it made of? The obvious follow-on question is, how does it grow? And then another question we're looking at, which again is difficult to answer and has not been done before, is what is the third dimension of the magnetic stripes? Now, many of you, in the audience, I'm sure know the whole idea of the magnetic stripes on the ocean. We've known that for many years. But what is the geometry of those stripes at depth in the third dimension? And again, this crack is a place that we can try and address that question. So, moving on to the next slide, you can say, okay, you got the questions, how are you going to answer those questions? And so, to try and illustrate that, let's talk a little bit about how we think oceanic crust actually forms. And really, there was a big revolution in the 1990s, because prior to the 1990s, and I'm going to draw on these things, once I get my pen back, is people really modeled ocean crust on continental magma chambers, and they simply assumed, oh, well, there must be a big magma chamber that's 5 kilometers thick that creates all the gabbro. But what happened in the 90s, seismology got good enough, people went out and did seismology over ocean ridges, and it was a whoops moment. What they found out was effectively the melt lens was tiny. You can see that little red thing that I ringed, that the melt lens was only 2 kilometers wide and only 200 meters thick. So the question became, how can you form 5 kilometers of gabbro when the melt lens is only 200 meters thick? And so these two end members have been erected, and they've been hanging around for a while, but nobody can totally agree on which is the right answer. But one model is the so-called gabbro glacier flow model. And the idea of that is you've got this little melt lens that I mentioned. And then what happens is, you've got this continual supply of melt. So imagine melt continually coming in as you pull the plates apart. The melt ultimately freezes, forms a layer of crystals on the bottom, and you just get layer of crystals after crystals after crystals. And what's happening is the crystals on the bottom are flowing away like a glacier. Hence the gabbro glacier flow model. The crystals it produces form a mushy layer on the bottom that flow away as you separate the plates. And so that was really the geophysicist model. But the geologists who were working in things like ophiolites in Oman basically said, the seismologists are wrong. We build oceanic crust by just having lots and lots and lots and lots of sills go into the crust. And it's just that you can't see the black ones. I'll clear it. You can't see the black ones because, the red one is somehow making it harder for the seismic waves to get deeper. So people still argue over these things. Are we fundamentally building ocean crust by just injecting sill after sill after sill, or is there just one sill which then leads to this gabbro glacier flow model? And there are more complicated models out there, but these are the two end members that people debate. And so, moving on to the next slide, I can kind of show you what we did, and this is a figure from the proposal that we put into NSF. And the middle part is basically the figure you just saw. So on this side, here's the gabbro glacier flow model, and on this side, here's the multiple sill model. And then on the left and right of that, there's various little cartoons which basically show you how, in principle, we can distinguish between the two models. And if you look at them, you can see a whole bunch of different colored lines which represent different properties that you could potentially measure in the rocks. Now, I don't want to go through them all, but I just want to go through a couple to illustrate the issue. The question, illustrate how it might work, is if we've got the Gabbro Glacier flow model, basically a Gabbro at the top actually flows less than a Gabbro at the bottom. Just look at the length of the lines. And if that's true, then the rocks at the top have seen less strain than the ones at the bottom. So the Gabbro Glacier flow model predicts increasing strain with depth, which was the blue line on the right until I drew over it. Whereas the multiple sill model would just basically predict the same amount of strain with depth. So in principle, if we can measure strain in the rocks, you can distinguish between those two models. And then similarly, if we briefly look at some of the other curves, the Gabbro Glacier flow model would predict constant composition with depth, that's the green line, and there's the Mg number, the magnesium content of the rock. Well, the bottom line of that, if you've got melt coming into the same lens all the time, it's steady state, and so the composition should be the same. Whereas the multiple sill model will predict increasing Mg or increasing magnesium content with depth. Again, something you can measure in the rocks we're collecting and potentially tell the difference. And then the other curves on there, they have predictions for different cooling rates, different orientations of the magmatic foliation, and different age predictions. Again, this one would say effectively constant age with depth, the black line, and this one would say young. So, that's what we're trying to do. We're collecting these rocks from the top 2 kilometers of the green layer, which corresponds to the yellow layer in the optical pictures, and then ultimately we'll take rocks back and try and, measure these properties and basically distinguish between the two models. So that's what we're doing. So now let's look at some of the data we're collecting. And the biggest scale data we're collecting is just simply a map of the seafloor. And here's the boat we're on, the Atlantis. I took that in Easter Island, and it moored offshore. Easter Island is so small, there's no dock. So we had to get aboard by a little fishing boat, and a bunch of people enjoying the waves in front of it. But one of the things we can do with the ship is we can sail around, and what this is like a plowed field. What you're looking at, you see this kind of jagged edge on the top. These represent traverses of the ship. And so the ship is, doing this sort of pattern, plowing the furrows in a field, if you like, measuring the topography of the seafloor. And it uses a system called Multibeam. It's, basically sound waves. And then basically on any one track, the ship can measure a 12-kilometer wide swath of the seafloor. And again, you can see our map of Pito Deep, the blues in the middle. And you slowly build this map over the time you're here. You get a bit of spare time, there's nothing else going on. You send the ship out to basically, fill in a little bit extra of the map. And so tonight, we'll actually fill in this area and hopefully complete this area. We're nearly done. Actually, tomorrow night, we'll fill in this area and this area and be close to finish the map. Now, the important thing to say, or the final important thing to say about that picture, is the resolution is about 60 meters. In other words, we can resolve objects bigger than 60 meters on the sea floor. But our next tool is a thing called Sentry, which is an autonomous vehicle. And so Sentry, we drop over the side, it goes to the bottom of the seafloor on its own, and it sails above the surface of the seafloor at about 100 meters, and it makes the kind of maps that you can see above. And this thing basically has a resolution of 1 meter. So if you like, Sentry is our headlights. Because what we're doing is you put Sentry down on the seafloor and it finds you your rock outcrops. We can resolve anything bigger than 1 meter in size, and so it's perfectly, it's perfect for finding where the rocks actually are. And so then once we've done that, and I think you'll see Sentry when you get a tour, she's on deck at the moment. Once we've got that, we can then decide where to precisely put down the ROV, which is Jason. And Jason's in this picture. If you look down here, this is one of Lucas's clever shots. He basically took Jason being launched several times. So there's only one submarine really, but what you're seeing is 6 snapshots put together that here's Jason going into the water and then swimming away. Basically, once we get the Sentry map, we can target Jason, which can't move that very far, to go down, and it's a tethered vehicle. I think you can see the tether in the middle. Basically go down there to pick up rocks. And if you look at the picture on the left, you can see some of the work we've been doing. In the background is the Sentry map, and all those red dots are all the samples that we've collected. And in fact, we've collected even more. We're actually coming back at this moment from having done one final traverse in this area, which did something like that. So the whole point is we can do what a continental geologist would do, which is map at the outcrop scale the seafloor. This is a relatively big chunk of gabbro. It's about 1.5 kilometers across and 1 kilometer in vertical. This distance is actually 3 kilometers, but it corresponds to 1 kilometer vertical. And literally, we've been producing the most detailed map of the upper gabbros of the upper oceanic crust that's ever been made. So let me get rid of that, move on to the next slide. And here's an example of one of the rocks we brought back. Some of you might know the Stillwater intrusion. And when I saw this rock, I just went inch-scale layering like in the Stillwater intrusion. What you're looking at is a troctolite. The white stuff is plagioclase, the black stuff is altered olivine, and you can see the layers in it. This thing's about 1 foot across. And it's just a fabulous specimen. Lucas actually made a 3D reconstruction of it. So we've actually got a 3D reconstruction of this. We can revolve around and actually, keep that as a way of preserving the original before we start cutting it up and, grinding it up to do chemistry and whatnot. On the top, it tells you how many rocks we've got so far. We just passed 401 this morning. So we've pulled back 401 different samples from the seafloor. And to give you an idea, that's about 4,000 pounds. Jason, the ROV, can carry about 250 pounds each load. And again, really just coming back to what I was just saying, here's that map again on the left, but this picture puts it into a context. On the right is El Capitan. Just recently, the last couple of years, a couple of climbing geologists have basically mapped the face of El Capitan as you would do a geological map. And so in a way, the area we've been working on is just a little bit bigger than El Capitan. So it gives you kind of a feel for what we're trying to do. We're trying to do a similar geological map for the area we're in. And you probably can't read it, but what we've started to do is we've got all these traverses by the submarine. It's for fun. We started naming them after the famous climbs on El Capitan. So, at the top here, and again, you probably can't read it, but I'll bring it anyway. We call this traverse the nose. You can see a bunch of white dots that go down there. And then there's a bunch of red dots, which are actually waypoints rather than the samples, which we call Tangerine Trip. So we started to name everything after famous climbing routes. So that's kind of what we've been doing, but there's 2 more things I just want to mention. I mentioned at the start, the other thing is the 3rd dimension of the magnetic stripes. And here's just a picture of the Pacific Ocean. Everybody knows this picture. The oldest oceanic crust is over here. On the right-hand side, it goes back to about 200 million years. Here's the East Pacific rise, effectively 0 million years. And how do we know that? Well, we know it because of the magnetic stripes. We map stripes, and we can effectively date stripes. And so what we're trying to do, to finish off, is to get that 3rd dimension, as I mentioned. And so, here's a picture of a ship like ours sailing along, and as it sails along, it can measure the Earth's magnetic field. And that's how we've got the stripes, and you can see the stripes in this cartoon. But the big question is what's happening in the vertical dimension. And the picture kind of gives you a reason for the importance, or why it's important, is notice the red area is the shape of the magna intrusion zone, and basically the magnetic stripe is going to reflect that. Thankfully, the magnetic stripe becomes nicer. So if we can measure the shape of the magnetic stripe, then we put big constraints on the shape of the magma accretion zone, which is why we're trying to do this. Final thing we're doing, and this is kind of exciting, and this is kind of breaking news, is we went to this place, which is just about, about 30 miles south of us. It's called Pito Seamount, And effectively, it's where the East Pacific rise is meeting the edge of the Easter Microplate. And this thing is about 10 kilometers north-south. It's about 10 kilometers that way, 6 kilometers this way. And 23 years ago, if I go on to the next slide, some French people went there in their submersible called Nautilus, and they found a black smoker. And so nobody's been back to this thing for 23 years. There is the black smoker. It's a pretty low resolution photo because, you know, that kind of technology in 1993 wasn't great. And so we decided, well, you know, we got a ship. We can do what we like with it. I shouldn't really say that, but to some degree that's true. Let's go there and see what we can find. And so we took Sentry there, never been done, there about 3 days ago, and we mapped the surface of Pito Seamount, and basically we found tens to 50 of these chimneys, and there must be many more than one active black smoker. And so the project, and I remember talking to John about this, it turns out we're going to dive on it at 8 o'clock tonight. We've got 24 hours to go and visit and do high-resolution 4K video for the first time of these hydrothermal vent fields, which, you know, basically we've discovered. Prior to us, there was only one chimney known, and we can see from Sentry that there's at least 50 there now. So that's me done for a minute. You can ask me questions when Lucas and Teresa come back, but they're going to give you a tour of the ship, show you Sentry. We can't show you Jason because she's on her way back up to the sea surface, but hopefully you find it interesting to move back.
All right, thank you, Mike. So what we're going to do is we're going to head outside right now. As that heads up, we're going to go through a few metal doors, and Wi-Fi and metal doors don't tend to mix. So we're going to drop connection most likely, but you just stay there. We will pick it up as soon as we get on deck. Sound good?
Great.
Awesome.
There's a lag in case you got it. What is a black smoker?
All right, sounds good. So, welcome to the Pacific Ocean. As you can see, the weather is horrible right now. Yeah, just joking, it's amazing. Beautiful. This is Sentry. So, as Mike said, Sentry is an autonomous underwater vehicle. It's essentially a drone we pre-program a path into. At that point, we use weights to sink down to the seafloor. 24 hours, it uses these colored sphere to follow the path along the seafloor and create those beautiful maps that Mike showed you. In the 24 hours, it drops the weights. They're just iron, so they must weigh naturally. And it comes back and research where you pick it up again. Big on the top there. I'd also inspire you to that's a magnetometer on it. Sonar that's at the bottom. And it's this for redox chemicals, as well as temperature and roughness in the water.
John, can you tell them about the sound?
Also,
the resolution.
Because this quite clearly a Patriots fan. Sentry often gets decorated during the expeditions. That's this one. Right behind you, we have the other piece of equipment which is on deck. As Mike mentioned, Jason. This is one of Jason's elevators. So this is the device we use to make the sails from the seafloor back to the ship. As you can see, we've got a big float on the top. What we do is we take a bunch of those iron drop weights that you've seen once we use for Sentry, put them on the bottom, and then we bring it over the side of the ship, send it down to the bottom. Jason meets the elevator on the seafloor, 6 kilometers below us, and Jason open these up and put in the crates, which are full of rocks, take out these crates. At that point, Jason pulls that string there, which releases those droplets, and that big yellow float there carries it back to the sea surface where we picked them up, and the geologists inside the lab. So that's pretty much what's on the deck for the moment. We're going to head up to the Jason control bed at the moment. It's, as Mike said, on its way up, so we're just going to see a water column. But you do get to see how Jason's controlled and meet people in there, which is kind of fun. So we'll pass through some doors again, might drop connection. We'll see you in about 30 seconds.
Something's rubbing the mic.
Well, he is rubbing the mic. The mic is attached to his shirt.
Yeah,
it's attached to him.
And I think it's wind.
Yeah. Partly, but it's also how he moves his head. He's moving the mic. Yeah. All good.
Given that it's coming from what, 5,000 miles away, I'm not complaining.
John, what's the time differential?
Not much.
They were 2 hours ahead of us 2 days ago, so I'm sure they still are. But when you look actually at the time zones, it looks like it should be exactly the same as Mountain Standard. There, the Galapagos, but they were on 2 hours ahead.
Definitely lost him. Hey, John, how are you thinking of handling the questions?
Yeah, black smoker is a superheated mineral land water, a spring, hot spring. So it's full of magnesium and all kinds of other minerals, and that, that's what gives it the iron, the black appearance.
But really hot.
They can be hot enough to. Here we go. Hopefully.
All right, are we back?
Yep, we're back.
Awesome. So as you can probably see in here, it's a lot darker than lighter here. We're two pairs, which would be and as you can see around me, I'm surrounded by restrictions. These are the live feeds from Jason, which are transmitted back up to the ship through that one cable, which connects the ROV to us. And there are usually 6 people in here. Because we're just up in the water column coming back to the ship, it's a few less people. But I'll go through each of their roles so you can sort of see what they do. In the center, we have the pilot. The pilot is responsible for essentially moving the ROV Jason itself. You want to give us a brief explanation of what you do, Scott?
So from here, all the controls move Jason. This is the control box. A little bit bigger, but this moves.
Can you ask him to get closer to the mic?
This controls the camera.
Too far away from the mic.
Sorry.
Oh, hi. Sorry. So this is the control box. This controls Jason. It has 2 different joysticks that control Jason. This joystick controls the camera, so I can look around as I need. This one goes left, right, forward and back, and also twist left and right. This joystick is what goes up and down on Jason. It helps do. Then we have 2 manipulator arms. Manipulator arms are what we use to gather samples for science. And if you look at the screen here, you'll see this is the arm. This is what we use to grab the rocks. On this cruise, we use or to grab instruments like this. That's pretty tricky.
Awesome. Okay, cool. The pilot's left sits then here. Who's responsible for the other part adjacent to Medea? Tell us a little bit about Medea.
Medea is a part of the adjacent system, and it's hangs on the winch wire. And the engineering station that control the winch and help the pilot. So I provide the power and the amount of cable that's out in the water through the pilot up and the big rods and the science centers.
Speaker needs to be real close to the mic.
Thank you. To the pilot's right sits the navigator. To the pilot's right sits the navigator, who is currently out just because we're sitting in one place at the moment. And then behind all of them are the scientists. And we only have one scientist here at the moment. This is Rebecca, sitting in the watch leader chair. Rebecca's a student at the University of Victoria in Canada. Do you want to tell us a little bit about what you do, Rebecca?
Get closer to the carry. So usually is strictly in the water and they
I don't know whether it's their bandwidth or ours.
They have a map and they go down the ocean floor and say, let's go here. Usually I'm one of these two computers. One phone to take notes, see right now the Sentry, right now the outcrop and rocks are, right now observations and same picture, quiz, and we're the other one where we just take pictures to make sure we record everything that we see. Yeah.
Tell them what happened. The sound may still be connected.
Any questions? Oh.
I think we just.
Okay, sounds good. How much did we miss there?
Did you guys lose us? Or did you hear Rebecca talking?
No, that we lost.
All right. So we'll bring you back.
Whoever's speaking needs to be really close to the mic.
Speak slowly.
All right. So we'll bring it back to Rebecca here. She is currently sitting in the watch leader's chair, and she's one of the scientists on board the ship.
All right. So I'll just start over. So this is the watch leader's spot that has usually the head scientist of the ship. We have 4-hour shifts, so we're inside the control van for 4 hours. And then Jason's in the water. In the watch leader chair, they tell the pilot what straps to select, which example we want to take, and hopefully get everything. And then we're going to this. I usually sit in these 2 chairs right here.
Slowly and real close to the mic.
Okay, so I usually sit in these 2 computers. One of them takes notes about the samples we see, lights we see, the kinds of outcrop we see, so field notes we log, and then our computer will take pictures, so we can record everything that we see, and take videos so that we can show important highlights of our sampling process, so that we can later go back and make sure we have the right rocks, go back and make sure that features we saw are really there.
Awesome. Thanks, Rebecca. So we're going to head down to the lab right now and go see Mike and Bobby again and give you a chance to ask them questions and learn a little more about the rocks collecting.
So if somebody wants to ask a question, I guess what you'll need to do is come up to this camera here and put your face in front of it and speak into it.
John, is it easier for you just to read?
Or do we tell you and you tell them?
I don't want to get into the cycle.
Okay.
And hopefully the connection will be as good
Yeah,
as the
hopefully
mic
it'll be stable.
was talking earlier. I'm amazed this works at all. Honestly.
Yeah, the ship is not exactly stationary or not bobbing around.
Well, I think this is bouncing off of the satellite somewhere. Maybe multiple satellites.
The geology talk was really good.
Yeah.
The Gabbro.
That's the best I've ever heard. I mean, that was all new to me.
Yeah.
He's back.
Welcome back. I hope you guys enjoyed the tour. So what we'd like to do now is, especially since you couldn't see operations, because unfortunately we're coming up, is Lucas and Travis to make this really nice video, which is actually on our website. I'm just going to play this. It's just 4 minutes long. It just gives you a feel of all the steps involved in launching the submarine, etc., etc. So Lucas, well.
So there they are sampling on the seafloor. Yeah, they're kilometers down.
6.4 kilometers.
Not 200 meters. Yeah, they don't have. That's the way it is.
Wow.
So send it off the cable.
Never thought that was cool.
This stays down, just keep sending stuff off.
Just like to show you, here's literally a rock that was split. Typically we collect the rocks and then we split them to be able to see what they're like. Here's one that was basically collected last night. We split it this morning, I just wet the surface, and I kind of just like this one with some troctolite. And what you can see is all the black things are all they're altered, that's why they show up black. But if you look, you see a tremendous variation in it's been the place layers, and then you can see you guys are chasing me with the camera, so and you can see the green, enormous green hydroxide. So you know, it's one of the kind of more extreme examples of what we're bringing up. But this is the stuff that makes ocean crust. And magna, Lucas, just to show us the table, isn't more normal. This is so there's a table with all the samples from last night and the day before. This is kind of numbers 300 to 365. And this is, how we process them. They're brought on board, they're measured, they're weighed, they're photographed, then they're split, and then that's oriented, and then the split surface allows us basically to better identify the minerals, and so then we do an inscription and so on and so forth. And Bobby, who's here, just handed me this one, which is just a much more boring standard troctolite. What you're seeing is black wallaby, white plagioclates, and it's actually one of our big results. This is a relatively primitive rock. There's little pinoclops in there, whole chunks of what we've been surveying, which is the upper and which crust is made of. Which is a surprise. It comes back to those curves we talked about earlier. Basically having such primitive rocks close to the surface is something that's not predicted in this. But we just thought we'd show you. I'm going to walk away and just introduce you to Bobby, because some of you know. She's here too. She's another one of the coaching scientists. She's going to say hi, and then we'll answer questions.
Well, hello. I've met some of you when I lectured up there for the geologists Dr.s a couple of years ago. John Capitan graciously hosted me, and I came to chat with you. I did talk about the exploring parts of the ocean crust, but at the time I was actually talking about slopes better than crust and large normal faults that actually expose that crust to the seafloor. So here, I think we probably explained very fast about ocean crust, and for us it's exciting because we have an opportunity to sort of compare and contrast what we see in slope spreading environments like the Southwest Indian Ridge or the Mid-Atlantic Ridge versus what we see in the Pacific Ridge and the Pacific Ocean, the global ridges. So anyway, I think now is our opportunity to ask if you have any questions. Thank you.
I'm being back in the basket.
So come right to you. To the camera.
Start speaking.
So go ahead and just give you the camera.
What is the significance of the vents?
Oh, well, so the easy answer to that is that they're kind of, spectacular things, which in some ways, to some people, are more interesting than the rocks. So, let's just go back a step. You briefly saw pictures of the submarine on the sea floor, collecting rocks. That's important. As geologists, that's what we've got to do. But after a while, if we've been watching that kind of thing happen, after a while it becomes a tad, unspectacular. But if you go to the vents, you're seeing dynamics in the bottom of the ocean. The vents, if they're alive, basically are smoking. That's what they call black smokers. They're basically ejecting clouds of stuff that looks like black smoke, but it's actually full of little particles of this color. And their importance is they're host to a completely different ecosystem of animals. So you find one of those, not only, you've got rocks down there and you've got this dynamic chimney, but you've got a fauna down there that is very different to the fauna on Earth, because at the bottom of the ocean it's dark. And so that whole ecosystem down there is based on the thermal properties of the system. The temperature of black smokers is about 400 degrees C. So you have bacteria living down there, and then animals living off of bacteria, and so on. So, one answer to your question is that, in a way, they're much more spectacular. And, as chief scientists, one of the things that I wanted to do, we've got a whole bunch of Wyoming students on board, undergraduate, bunch of grad students, and other grad students. And these guys even, probably, a lot of those guys will never go to sea again. So it's just a nice opportunity to get a trip to show you. So that's the kind of tourism bit. But there's good science there as well. I mean, the big issue is we know so little about seafloor of the oceans, because to explore it, you have to do what we're doing, send submarines in. And so, as I mentioned at the start, we basically discovered these hydrothermal vent fields just 2 days ago. So part of the background is just, general exploration and discovering what's on the surface. And the very last part of interest, or actually I can do a whole bunch of stuff, but one thing is that they basically are sulfide deposits. And so, sometimes in the future of the Earth, after we exhaust some of our minerals on the continents, potentially we could go to the ocean crust. Maybe not these active sites where animals live, but we can go to the dead ones, mine it, so that some of the methods can be on. So, there's an economic influence to know where these are. There's a sort of life evolution aspect of it. Some people believe that life evolved in similar conditions that the planet Earth is actually. So there's a whole bunch of science in there. There's a whole bunch of exploration, scientists, because they started with, the other side of the brain. Everybody on the ship grew up and sort of excited to see these things. And so Jason, Matt, if we find them, we should. We'll be full of people, I guarantee. Just watching, just a second.
Just to add one little note, even today, although it seems outrageous that we might consider mining some of these sulfide deposits on the seafloor, even today, countries are actually going into international waters, staking claims along parts of the mid-ocean rim. So I know for a fact that the Russians and the Germans have a number of claims living on the Mid-Atlantic Ridge, 13 degrees above latitude. I was committed to French actually 3 years ago, and the Germans came along with their sort of autonomous robotic sort of fish to see if they could actually image these lactovers. We did the mapping, we did the sniffing, and we found some that we dove with the French ROV, and we actually saw them with their temperatures. We actually sampled the sulfides themselves, and had microbiologists with us as well, who were looking at sequencing the DNA associated with the systems. So I know for a fact that there are countries around the globe that are very interested in time, so they have claims to stake. So that's an add-on to my comment about
more questions? Sorry, I can just see the back of an iPad, so I can't see you guys.
Just another quick, 2 questions actually. Is there, the old deep sea drilling project that sail around, did they ever actually drill in this area? And if not, could you ever come up with a submersible drilling unit? Because it seems that what you really would want is a nice couple of meter or couple hundred meters of core that you could pull out and actually bring back and look at to get your answer. The second question is, we're going to be going to Iceland later this year. Could any of the research you're doing here be done on Iceland?
Okay, so the first question is, as many of you know,
Speak slowly and real close to the mic, Mike.
Sorry. The drilling project has been around for a while, and people have attempted to drill deep into the Galapagos crust. And it quickly gets complicated. The deepest hole that's ever been drilled in deep crust it's actually been done in the Indian Ocean, and that's 1.5 kilometers down. So those guys brought back 1.5 kilometers of gabbro. But the slow spreading crust is kind of different to the fast spreading crust where we are. And in the Pacific, they've tried, but they've had kind of less success. There's been actually a lot of attempts to try and start drilling all the way through. And the biggest problem is the salt from the top are very unstable. And so you start drilling a hole, and the whole nature beast is you actually can only drill for the economics of the system is you drill for a couple of months, and then the chip goes away, and then the chip comes back, and in that time the holes can decay. And so the kind of deepest hole in the Pacific has made it through the salts and the dikes, but it's only just kissed the top of the gap. So, it's a lot cheaper, even though, to give you an idea, this cruise is about $3 million, it's a lot cheaper to do it this way than to drill a hole. The next part of that question was, could there be a seafloor unit to do it? The terrain we're actually in is kind of very steep. So the truth is, I think that might be difficult. But, you know, you could bring the drill ship here if you had enough money. You know, in principle, the ship could sit on the sea surface. You know, it can drill into up to 6 kilometers of water. You know, here, if we started on the sides, we might only have to start drilling, let's say, 3 kilometers down. We could have a go at that. You know, when it comes down to writing a drilling proposal, in principle, and it often takes many years, but it's a big process, is that, you know, we can sit here and write a drilling proposal and try and get the ship to come back.
Just as an aside, there are what are called seabed rock drills. The German government has one that's based in Bremen, Germany. It's called MEBO, the Meeresbodem drilling. And it can potentially go, as you say, potentially up to 150 to 200 meters water depth or depth below the seafloor. But in these kinds of rocks, especially if they're fractured, it's been quite challenging. Similarly, the British have another seabed rock drill that can potentially drill to 100 meters below the seabed. So the technology exists. It's pretty young. It's pretty poorly explored in these sorts of terrains. It works beautifully in sediments, but in hard rock, it's
Okay, so another part of that question was, what can you do there at Pito Deep that could not be done perhaps in Iceland at the surface?
That's a good question. As it turns out, there's an easy answer to that, but there's a more difficult question hidden in there. Iceland, I don't think there's this much gap row exposed. You need the kind of tectonic window to be folded to let you get into the gap rows. I mean, you're absolutely right. If you're interested in the lavas or even the dikes, you can wander across the surface of Iceland and do it more easily. But there isn't the kind of sections that we've got here, which potentially have 2 vertical kilometers through the gap rows. The kind of follow-on question to that, if I can ask myself a question, is you guys all know about ophiolites. So a good question would be, well, why do you have to spend all this money to do it in the oceans? Why do you do it on ophiolites like the ophiolite? It's probably the best one in the world. And that's a really, really good question. There are some reasons why it's better to do it here. It turns out there's a big kind of debate about ophiolites. Are they true ocean crust? Did they form at a mid-ocean ridge, or did they form, say, in a background basin? So people kind of argue about that. In truth, probably some of them did form at mid-ocean ridges. A lot didn't. They're enormous bits of hot crust behind island blocks that got caught up on the island block and slammed into the continent. But another good reason for working out here is just very simple. We know where the ridge is. Imagine if you had a piece of ocean crust in front of you, gabbros beneath dikes, beneath basalts. Was the ridge on the left or the right-hand side? And, again, people will often argue they know from ophiolites, but you've got no direct evidence. And, we saw some of the questions I was asking, which way does the foliation dip? Does the foliation dip in the rocks away from the ridge or towards the ridge? That's an inherent part of those models. If you're doing it in the oceans, you know where the ridge is. And so one of the things we're doing is, mapping the orientation of the land, etc., and, giving its relationship to the ridge. Can't really do with certainty.
Another question here.
Yeah. Get right into the mic.
Have you been able to determine whether the source of the mid-ocean ridge spreading is from the multiple sill theory or directly from the upper?
I guess one of, I think I can kind of say this. One of the most obvious things we found so far, remember we were talking about geometry of magnetic strikes. The multiple sill model kind of requires a kind of vertical strike. The extent of it will be vertical for the crust. What we've kind of seen in the rocks here is the boundary of the strikes is almost sub-horizontal, which in some ways is a shocking result. What that means is nice enough. It just means that the whole region down there was very, very hot for a long time. And that fits much better with a gabbro glacier flow type. Basically, it means most of the heat is lost from the top of the crust, hence you end up with a big wide hot zone, hence you end up with a very shallow looking ice. So, based on that one piece of evidence alone, I would say, what we're finding points more towards some variation on the gabbro glacier flow. It can't be as simple as that. Rocks are too complicated, but certainly on a big scale, that's what we're seeing.
We'll get back to it.
If we would like to invite you out for a talk in 2018, put you on our schedule, maybe talk about the Pito Deep and its cruise, and maybe bring some samples along.
We'd love to do
Yeah,
that.
that sounds great.
We did another one of these broadcasts, and they said, well, how long is it going to take you to analyze the rocks? And my answer there is years.
The rest of our lives.
I mean, really, there's only 50 inside this on the chair. And that's one of the nice things with this small group of people. And, as I mentioned, we've got 400 rocks so far. There's the black smoke samples, which will come up tomorrow, hopefully. I mean, we will probably, that's not me trying to decline your answer, your invitation. Thank you very much. We'd love to come up. We'd be delighted to. But just a comment that we'll probably be working on these rocks literally for the rest of our lives.
Another question, when you pick up a rock, how do you know that it didn't fall from somewhere up above, like from a rock slide or something?
Yeah, no, in some cases you don't know. But actually very, very rare. If you remember back to what I talked about, that's the beauty of using that triple system that I talked about. We send Sentry down to basically find the outcrop. So, I can pass the question back to you, how do you know when you pick a rock from the surface of the earth, whether it's from outcrop or it's fallen down? Basically Sentry gets us to the outcrops, and then with the submarine, we try and literally pull off, we might use a hammer, but we try and pull off a piece. It's all video, and so what happens is every rock that comes back on ship then gets reviewed through the video, and we make that decision of whether it was talus, whether it was, on outcrop, what we say, it looks like it came from there, but it was a loose piece on top of the outcrop, or whether the submarine actually pulled it off. And the kind of exciting thing, because it is important we can do this, is I would say 60 to 70% of our rocks are from outcrop.
Yeah, I would say at least we have a very high proportion. Really fortunate curve pilots with Jason who will just persist at trying to get the claws on something and pull it out from the outcrop or flake it off of the outcrop. So we've been incredibly lucky, and I think that is another sort of unique aspect of the samples. They are, in fact, the majority in situ samples, which is unprecedented.
Because just quickly to add, you need that if you're going to use the orientation of the fabrics to answer the question. If you've got a random ball around rock, it tells us nothing about what the orientation was when it formed apart. Most of our samples.
Okay, thank you, that's great. Someone else?
Thank you very much.
One quick one, is there any thought of having Jason equipped with moral equivalent of a rock hammer and a rotary diamond bit drill?
Rock hammer is a little difficult because the whole system is neutrally buoyant. So can you imagine the trial, and the arms can't move very fast. So if you imagine it trying to swing a hammer and hit something, and all it does is just push the submarine away. That's what would happen. But there is actually a small drill that you can actually attach to the bottom of Jason to do just what you applied. One of the things that just comes down to time budget. It takes some time to have this thing drilling this little piece of ore. And frankly, it's a lot quicker to have these incredible arms that Jason has to just attach to a rock and yank it off. You can do that a lot more quickly than you can drill a core. The drill they build only goes to a few inches anyway. One other just factoid, which I think is fun, is you should never try and shake it in the hands of the claws of an ROV, because basically they are so strong that if it closes jaws on your hand, you will have the distant place.
So obviously there's a lot of life near these black smokers. Do you ever see other life away from them when you're out exploring?
Yeah, we showed you a couple of pictures in the video. Not much. These depths in the ocean, and we're at 5 kilometers down. There isn't a lot of life down there, but there is life. And, probably whatever life is down there gets the shock of its life when Jason turns up with all his headlights. But it is one of the fun things about what we're doing is that we intentionally find new creatures that people have never seen before. We catalog them. We don't sample them obviously, but we try and take video. It's a bit difficult. This creature swims past you and you're trying to follow it. And the fact tracers keep in the list of all the things that we found, a little photograph album, which when we get off the ship, we can try and look up and see, or at least get their proper names, and actually see if we found anything, completely new. It is a high probability that there are many creatures down there that around the world that no human has seen before. So that's just another fun thing of what we're doing. When you look at boring rocks, and some a Dumbo octopus or an octopus flies by, it catches everybody's attention.
Is the visit to the Seamount and the smokers, the hot springs, basically the end of the cruise, of the research part?
Yeah, we've got today and 2 days left, and so the plan is the moment we're recovering Jason, we're actually a little worried about weather, believe it or not. Not that it's not 80 degrees out there, but basically, we get the effects of big storms at 50 degrees south. We're 23 degrees south, so we're a long ways away. So we don't get the storms, but what we get is the swell. And if the swell gets too much or too confused, and the boat is bouncing up and down, then we can't launch the submarines. And so we're, nervously waiting. It isn't impossible that the swell, if we just are about on the edge, basically terminates us for the last 2 days. But the plan is, assuming the swell is good, is Jason will go into the water at 8 p.m. tonight, spend 24 hours mapping the black smokers, and then we'll come back up to this site, launch Sentry for 24 hours, and then we leave at Sunday morning at 7 a.m.
All right, well, you've given us your hour, more than. So this has been really great, and about half the time the video has been good. It was really excellent right at the beginning. It was super resolution when you were giving that presentation, Mike, and it's been sort of off and on since. But we really very much appreciate you and the RV Atlantis crew making this possible for us. So thank you very much.
You're very welcome.
And I'll just wish that by the time you get back to Wyoming, this series of winter storms, you can find a way to stop them from rolling it out in the Pacific. And we need some sort of clear blue sky winter weather.
I'm looking forward to it. Thank you guys very much as well for inviting us. And just to say, we'd like to come next year if you'll have us.
We'll see you again sometime.
All right. See you